measurements, taking accurate measurements, how to do unit conversions with measurements. We're going to do a lot of talking about significant figures or significant digits, scientific notation. All of this kind of stuff for Chapter 2 gives us a good basis to move forward into the kind of quantitative or mathematic portion of chemistry. Okay, so it allows us to learn how to take accurate measurements, learn how to add and subtract, multiply and divide those measurements with correct significant digits or significant figures, and that has to do with accuracy and precision of your measurements, and how to convert units between the U.S. system and the metric system and things like that. Okay? So to get here, we're going to briefly talk about the scientific method. These are all things that are a review to you, okay, a little bit more, so you don't have to write this down word for word. Take what you need, okay? So most of you could name steps to the scientific method, right? Your hypothesis, your procedure. We could name those things to the scientific method. That's not what we're going to go through. What we're talking about here is why do we have the scientific method? Why did we form it? Okay. The scientific method gives us an approach to solve problems. Okay, so if we identify a problem or we ask the question, we have to find some logical approach and some steps to basically solve this problem or to answer the question. Okay, so we do that by making observations and collecting and analyzing that data. So the way that we do that, the way that we make observations and collect that data is by having or conducting an experiment, right? Okay, that should be a very, very common word throughout your science classes. Okay, an experiment is a procedure that would carry out under controlled conditions. Why do you think that I kind of put controlled conditions in bold here? Why is that important? Somebody raise their hand and tell me why that's important. Jack, what do you think?
Because different types of conditions can yield different results.
Yeah, very good. Different conditions can yield different results. So I can't just throw all of my reactants into a beaker and try to see what's happening, right? I don't have any control over that experiment. I have to control maybe the temperature. I have to maybe control the speed of that experiment. I have to control one of my variables so that I know what's doing the reacting. Okay, I can't just kind of take a look or take a glance at things that I don't have any control over. Okay, I have to control conditions in order to make my observations. I have to know that something is staying steady in order for me to measure that change that's happening. Okay. Once we collect our data, we look at patterns and relationships that have come to the surface because of this experiment I did. Okay, I want to look at patterns and I want to look at relationships between my two variables. Okay. From there, we make our generalizations, or we develop our theories, or we try to develop a law, things like that. We talked about models, theories, and laws in that first chapter. But that data that I collect based on my observations is going to give me an idea once I can view these patterns or see these generalizations. So an example of these generalizations that might be made is, let's say, when I heat something up, right, maybe it dissolves faster. Okay, I'm controlling the temperature increases. So I might say with every 5 degrees that I increase it, it dissolves at a rate of 2 grams per second faster or something like that. Okay? Those are the types of generalizations that we could be making. Okay? Does that make sense? Review so far? Okay. These data that have been collected before, or collected previously, generalizations that have been made previously, give us the idea to formulate our hypotheses. Okay, multiple hypotheses. And your definition for a hypothesis, I know that's the plural version there, but the definition of a hypothesis is a testable statement that's based off of previous data. It's really important that it says it's a testable statement. We should word hypothesis in the if-then form. So, if I increase temperature, then I think my substance will dissolve faster. Okay, if I make it colder, then I think it's going to slow down. Okay, that's that if-then format. Is that familiar? Okay, very good. If-then. Okay, so hypotheses have to be written in if-then statements. Have you guys done that a lot? So in statement, the then portion is basically what you're testing, right? That's the basis for your new development or your new data. Okay, that should be what you're looking at. So you formed your hypothesis, now you're going to test your hypothesis. And this is kind of what you're looking at. You undergo that experiment or you begin your experimentation to provide data to support or refute a hypothesis. What does it mean to refute a hypothesis? To prove it wrong. Good. Right, to prove it wrong. And these are just a couple vocab words that go with your scientific method and your experiment kind of chunk of this chapter. Controls are any condition that remains constant, right? If we're in the control group, that means that you are not undergoing that test, essentially, or you're staying constant. You're going with whatever had been previously done. If you're in the variable, then you are being changed, right? There's some change that's happening. Variable. So within these variables right here, you might put a little note under there for independent and dependent. Independent means that we control or we manipulate that variable. The dependent variable depends on the independent. Okay, so the independent variable is the one that we control. The dependent variable then depends on that thing. Okay, so if my hypothesis says if I increase heat or if I increase the temperature, then my reaction will happen at a faster rate. Which of those is my independent variable? The temperature, right? Because I'm increasing the temperature at certain intervals. I get to control that. I get to manipulate that. My dependent variable then is what? Yeah, how fast my reaction is going to go, or my rate of reaction. Okay, that's my dependent variable. If I look at my data that's graphed, if I put my data on a graph from this experiment, is everyone good with this slide right here? Can I clear this? Okay. So if when we have our experiment done, we've got our data analyzed, we have a result. What do they lead to? Okay, models, theories, and laws. Okay. Models, theories, and laws. And have we touched on these yet? Okay, I'm getting it confused with my other class then. Okay. Models, theories, and laws can come from the results of experiments. It says here that models are physical objects used to explain how phenomena occur and how data are related. Okay, it doesn't have to be a physical object. A model doesn't. It doesn't have to be three-dimensional. It could be some sort of visual model, just a drawing, a sketch, things like that could be examples. It doesn't have to be a three-dimensional model. Just keep that in mind. Okay, so models tell us kind of exactly what's happening. Theories give us a general statement that explains a phenomena. Okay, so we're going to cover things like kinetic theory, how molecules move. We're going to cover things like atomic theory, which is where electrons are located around the nucleus, things like that. Those give us a kind of a general statement and a general kind of explanation about why things move the way they do, or if we're in kinetic theory, where the electrons are located in a general sense, kind of in atomic theory. Those things give us general statements. The laws, however, describe the phenomena really concisely and clearly, but they give no explanation. Okay. Can anyone think of any scientific laws? Have any examples? Measurements can be taken lots and lots and lots of different ways. Can we think of a few examples of what types of measurements we might be taking in chemistry? Mass, good. Dom? Temperature? Volume of something, good. Sean, what do you think? You're going to say volume, okay.
Density.
Density, good. A combination of mass and volume, very nice. Uh-huh. Reactivity, somewhat, yeah. Not quite so measurable, but essentially, yeah. Good. Anything else? Those are good ones. Volume, mass, density, temperature, time, maybe if we're looking at reaction rates. But those are the big ones that we're going to be looking at here. Okay? We have to use a common way to measure things in the universal scientific world, right? In the worldly scientific practices, we have to have a common system. Do you think that people in Europe measure things in pounds or in ounces or in Fahrenheit? No. Okay. The United States has to be a diva and use their own measurement system. Okay, so now the United States has to work to convert all of their measurements to this worldly scientific language known as the metric system. Good. Okay, or the International System of Measurements. Okay, or System International. That's where SI comes from. Okay, so SI units is also called the metric system. SI stands for System International. Okay. But basically, we're going to look at the conversions between U.S. system and the metric system. I gave you here what it measures. It measures length. I gave you the full name, and then I gave you the abbreviation for it. Okay, so these are base units that you need to have in your notes somewhere. So let me explain what this table looks like first, and then I will give you a few minutes to get it written down. I want you to have from mega to nano. Okay, you don't have to go bigger or smaller than that. I want mega to nano, but let me explain kind of what this picture, what this table is telling us, and what I'm going to expect basically for you to look for here. Okay, the base, which means like the regular plain old meter or gram or whatever, fits right here in your table. Okay, so the base fits there. So that means anything above this is larger than the base unit, right? A kilometer is larger than a meter. Anything below this is smaller than the base unit. So a decimeter is smaller than a meter. Does that make sense? Anything above or below that line. Above is larger than the base, below is smaller than the base. Okay? what I would do for things that are smaller than the base, I like to rewrite them because I don't like to use decimals and I don't like to use negative scientific notation. Okay, when I'm doing unit conversions, when I'm doing things with the metric system, I don't like to use decimals and I don't like to use negative scientific notation. If you're completely comfortable with that, using conversions, great. But I'm going to rewrite it like this. I'm going to say 1 meter is equal to 10 decimeters. Okay, so instead of having this as a basically a decimal point over here, I'm going to rewrite it so that the bigger unit gets the 1. Right? A meter is larger than a decimeter. And since we can see right here that a meter is 1/10 of a decimeter, that means there must be 10 decimeters in a meter. Okay, are we kind of on the same page there? I know it seems like a lot of stuff going on right here, but then if I'm looking at centimeters, how many centimeters are in a meter? 100 centimeters is in a meter. 1 meter equals 1,000 millimeters. Okay. 1 meter equals 1 times 10 to the 6th micrometers. Micro is this little U with the tail on the front. Okay. No, it's a Greek letter M, but it's drawn like this. It has a little tail on the front, kind of looks like a U. Okay, that's micro. And then 1 meter is equal to 1 times 10 to the 9th nanometers. Okay, so that's just what I would put right here on my table if I was writing the table myself. Okay, and that's how I will do conversions. I'll always use I'll always give the bigger unit the 1. Okay, and that will make sense when we start looking at conversions here in a second. So we might measure area in meters squared. Volume, we already talked about, was the liter or the cubic decimeter. We don't use those a whole lot at least. Density is grams per cubic centimeter or grams per milliliter. These two are the same thing. A milliliter or a cubic centimeter are the same thing. Okay, if I want to go from Celsius to Kelvin, all I do is add 273. 273. That's because 0 degrees Celsius is equal to 273 Kelvin. Is it degrees Kelvin? Or just Kelvin? Just Kelvin. Okay, so that means if I want to go from Kelvin to Celsius, what would I probably do? I'm going to subtract 273. Okay, so if I'm at 0 degrees Celsius, that means I'm at 273 Kelvin. If I'm at 100 degrees Celsius, what's my temperature in Kelvin? 373 Kelvin. Okay, really easy conversion. It's not, we can't really even call it a conversion, but we do. We just add 273. The US to SI or metric system conversion. So this table you do need to have in your notes. We will use this one pretty often. Okay. So when I say a conversion factor, these are the relationships between these two that help us change from one to another. happen to connect the US measurement system to the metric system. When we're doing our conversions and when we're looking at converting these measurements between different units, our units are extremely important. Okay, that means we have to carry them throughout the entire problem. Okay, so today we're going to look at unit conversions. And what I mean when I say unit conversions is that we're trying to display this measurement with a different unit. Okay, that's the same measurement, same amount of substance, same length, all this kind of stuff. We're just trying to display it with a different unit. So we have to make sure we carry units throughout the whole problem to keep things consistent. Okay? Including units on our final answer shows us what was measured. Was it mass? Was it length? Was it volume? Was it time? Temperature? What was this number that you're telling me? Okay? So without units, your measurements make no sense. They're just numbers. So when you give me answers, make sure that you leave no numbers plain. Okay? You have to make sure that you are including those units onto your answer and throughout the problem. You will notice if you start to do unit conversions without units, you will become confused quickly. So just make sure that you take the extra 3 seconds to write down the unit in your problem so that you will eliminate, hopefully, that confusion. Because it's really easy to put numbers in the wrong places if you don't have the units correct. And all that a conversion is basically displaying a measurement with a different unit. Okay, displaying a measurement with a different unit. So a conversion factor is a ratio of two different units that can be used to convert one to the other. So a conversion factor is a ratio of different units that we use to convert one unit to another. If we had both labeled grams here, this fraction wouldn't be true. But we know 1 kilogram is equal to 1,000 grams. So our conversion factor here are things that equal 1, and it works because of the units. When we talk about conversion factors and we line up our fractions or our conversion factors, we will see basically which one needs to go on the top and which one needs to go on the bottom of this fraction. And I'll show you the system that I use to do these unit conversions. But basically it works either way. So you might look at this fraction and say 1,000 divided by 1 is not 1, but it is because of the units. Okay, that makes a big difference. Okay, so let's practice some conversions here. If I want to go from milligrams to grams, so here's my example. I want to convert this milligram measurement and I want to put it into kilograms. So I'm starting out with 142.2 milligrams. I want to see what that value is in kilograms. So let's just think first of all, is milligrams bigger or smaller than a gram?
Small.
Milligrams is really small. Is kilograms bigger or smaller than a gram? Big. So it's going to be a large number or a small number? What do we think? We're going to get a large number of kilograms? No, we're going to get a small number of kilograms, right? Because we're starting out with a really small amount. And we want to see what that looks like with a really big unit. So it's going to get a small number. And let's see why that is. Okay. So when I convert, I use something that's called a T-chart. Okay. And a T-chart goes like this. I always start by writing what I know. 142.2 milligrams. Then I draw a T. This is the system that I use for converting everything. Okay. And it will always work. So now we have to start just thinking a little bit. If I want to go from milligrams to kilograms, is there a one-step conversion that I can make? Take a look at your table. Is there a one-step, do you have an equals milligrams and kilograms thing on your T-chart or on your prefixes chart? No, but is there somewhere you could stop between those two? Where could you stop at between those to make it two steps? At the base, yeah, at grams, right? So now let's think about, I can't go directly from milligrams to kilograms, but I could go from milligrams to grams to kilograms, okay? And that's going to be our step. The good news is we can do it all in one process, and you only have to do the math one time, okay? So by doing the math one time rather than at each step, you're eliminating a lot of possible sources of error. So we want to just do it one time. So I want to go from milligrams to grams. What I'm going to do is I'm going to put milligrams here on the bottom because I want to get rid of it. And I want to go 2 grams, which means I put it on the top. Okay, and let me clarify. It doesn't always mean top and bottom, but it means opposite of where I started. So milligrams starts on the top, which means if I want to get rid of it, it needs to go on the bottom. Right? You can cancel things as they go here. So now I want to look at the conversion factor between grams and milli. Okay, grams and milligrams. Which of those is the bigger unit? Grams. So I say 1 gram is equal to how many milligrams? 1,000. Good. So 1,000 milligrams. So what I've done so far is I've canceled milligrams, and if I were to finish my T-chart here, I would be left with grams. Is that what I want? I want to be left in grams? I want to be in kilograms. So now I need to add another section to my T-chart. And I'll put grams on the bottom so that I can get rid of that. And I want to go 2 kilograms. Okay, so now between these, which is the larger unit? Kilograms gets the 1. And I say how many grams are in 1 kilogram? 1,000. Okay, so after we write what we know, these vertical, basically, columns of my T-chart should be equal to 1, right? They should just be the conversion factor. You don't do any math to go into these. You're just telling, basically, truths to put in these, okay? 1 gram is equal to 1,000 milligrams. 1 kilogram is equal to 1,000 grams. Okay, so without doing any math. So now I'm done. I've canceled grams. I'm left with kilograms. That's exactly what I want. Now, to solve my T-chart, I multiply across the whole top, then divide by the whole bottom. Multiply across the whole top, divide by the whole bottom. So you need your calculator out if you don't have that yet. So in this case, I take 142 times 1 times 1. Okay, so 142. Then I divide by either parentheses, 1,000 times 1,000, close parentheses, or I say 142 divided by 1,000, divided by 1,000, and then hit enter. Okay, are you getting a really small number or a really big number?
Small.
We should be getting a really small number, right? Times 10 to the negative third, I think.
E notation.
Okay, and E notation is scientific notation, right? Times 10 to the. To the negative fourth. Yep, I'm sorry, you're right. Okay, 1.42, and I could add another 2 on here. It doesn't really make a difference. 1.422 times 10 to the negative fourth. Or if you got this, 0.001422, same thing. Are we all getting that to come out? Did any of you get 142.2? Okay, the reason that would have happened is if you would have said 142.2 divided by 1,000 times 1,000. That won't work because they're both on the bottom. So these two are on the bottom here. So when you do it in your calculator, you either need to put parentheses around that or you hit divide by 1,000, divide by 1,000. Okay? But whatever's on the top of the T-chart, you multiply together. Whatever's on the bottom, you basically would multiply these together, then take that, the top divided by the bottom. Okay? Are we on the same page? Does the system make sense to everybody? Okay, you can do conversions lots of different ways. This is my system. It works for me. If you have something better that works for you, that's fine as long as I can see your work that goes with it. Okay, but this will be how I do all unit conversions. Okay, and we will start getting really good at T-charts later in the year too. Okay, blah, blah, blah. We already did that. Okay. We already did all that. Okay, let's try a different type of conversion here. How many seconds are in a leap year? How many seconds are in a leap year? Does it give us a number to start with? No. What do we know about a leap year? Yeah, it has 366 days. 366 days. So that's what I know, which means I'm going to write what I know. 366 days. And then I draw my T. So, I want my final answer to be in what unit? Seconds. So if I want to go from days, which is my beginning unit, to seconds, what's my logical approach to do that? Days to hours to seconds. You could go minutes to seconds, but you can go hours to seconds also, and we'll kind of talk about that. We'll do all of them right now, and then we'll talk about how that is. Okay, so now if I want to go from days to hours, okay, those two need to go on my T-chart next, right? You have to think about the steps you're going to go through, then both those units go in your T-chart. They need to go opposite of basically what you want to get rid of. So if days is on the top, it needs to go on the bottom on my second part here. Days is the larger unit. There's how many hours in a day? 24. So now I'm done with days. I'm left in hours. That's not what I want. Let's go from hours next to minutes. So 1 hour is equal to 60 minutes. Now I've canceled hours. Now I want to go from minutes to seconds. So 1 minute is equal to how many seconds? 60 seconds. So I'm done with minutes. I'm done with hours. Done with days. My unit that I'm left with is seconds, which is what I want. So now I multiply across the whole top, divide by the whole bottom. Should we expect a really large number here or a really small number? Really large number. Good. Take a step back and look at the big picture here. We should be looking at a really large number. Okay, somebody raise their hand when they have their answer for me. Yeah, Kiana, what do you have? 32 million seconds? Really rounded. Okay, give me a little bit more exact then.
31,622,400
Thank you. Do we agree? Getting that to come out? Okay, very good. When I talked that we could say go directly from hours to seconds, what's 60 times 60? 3,600. So we could always say 1 hour is equal to 3,600 seconds, right? We could go directly from there to there. We're not going to have to do hours to seconds conversions very often. You're going to have to do that in physics a lot more than you do it here. But you could make that shortcut if you so choose. Okay? Everyone understand the process of the T-chart? Okay, very good. I want you to try this on your own. We will do this last one here together as a class, but if you want to try it, you can. Okay, so I want you to try, this one also. Okay, you can do the first two on your own for sure. You can try the third one if you'd like. Remember on this first conversion, there's a couple different ways that you could solve that. So if yours doesn't match exactly the path that I chose, that's okay. How many of you went directly from feet to meters? Right, 1 foot equals 0.305 meters. That's fine. Right, that's a fine conversion to use. Okay, and it actually is one less step. I know it's the same amount of steps. So okay, so your answer might be slightly different than mine. That's okay. All right, so someone that chose the same path that I did here, do you have an answer for me? Yeah, Dom, what do you think?
77,248.512 centimeters.
Okay, do we agree? Okay, and for someone that chose the other method to go from feet directly to meters, can someone give me an answer for that one? Nobody use that method? Rachel, what do you think?
77,299.2.
Okay, very good. So in the scope of things, those are not that far off. Okay, so I know that seems like it might be a lot, but out of 77,000 centimeters, being 51 centimeters off is not that big of a deal. Okay, very good. For the second question, should we be expecting a really big number or a really small number here? A really small number, right? A nanometer is a really, really, really tiny unit. So I have 4 nanometers, which is a really small measurement. If I want to compare it to a kilometer, that means I'm going to end up with a really, really, really small fraction of a kilometer. Okay? Anyone have it for me here? Jenna, what do you got?
4.2 times 10 to the
Times 10 to the
negative 8.
-8. Do we agree? I had something I think a little smaller than that. Okay? Brett, what'd you have?
I had 4.24 times 10 to the negative 12.
-12. That seems a little closer. And let's see why. Okay, so as we plug this into our calculator, we're going to say 4.24 divided by 1 times 10 to the 9th, right, to the positive 9th, then divided by 1,000. Okay, does anyone here, give this a try? Anyone give the third one a try or have an idea? Okay, the only thing that's different here is that we have square units instead of singular units. Okay, so a centimeter squared is essentially, looks like this. 34 centimeters times centimeters, right? That's what centimeters squared is. The unit is squared here, not the number. Okay, and what do we usually see centimeters squared as a unit for? Area, right? This might be an area, a unit, okay? So centimeter squared is essentially centimeters times centimeters. So I'm going to make my T-chart, and I want to convert 2 meters squared. So I need my units to end up as meters times meters. So my conversion is really simple. I just have to do it 2 times. Centimeters to meters, and centimeters to meters again. Okay, so I know that meters is the bigger unit. I know there's 100 centimeters in a meter. All I have to do is do it 2 times. So I get rid of centimeters, I get rid of centimeters, and I'm left with meters times meters. So rather than try to memorize what the conversion is between area units, right, cubic centimeters and cubic meters, just do it twice, okay? So I'm left with 0.0034 meters squared, or 3.4 times 10 to the negative 3rd meters squared. We agree there? All right, very good.